Good morning, everybody. It's time for lecture number 6 in quantitative big imaging, and today I'm going to talk about shape analysis, and we're starting to go into the analysis of the images themselves. And why we want to do this is we want to quantify, we just not want just to see the gray levels. That is usually not sufficient, but we want to see really structures telling something about these structures. So the size, shape, maybe you want to even identify different clusters of sizes and shapes, or yeah, to make a possibility to give us a possibility to quantify and compare in our scientific investigation. Another thing is also how we can start creating some kind of describing simplified mesh, and that is going towards finite element simulations, etc., or even just doing pretty renderings. And what I'm going to talk about in this first part is a little bit why we're doing it. Then we look at characterizing these different objects, measuring volume, center of each element, or computing the extents, also looking into what anisotropy is. And first of all, we already seen this slide more or less a couple of times already. So what we have done until now is we have got our data, which is a huge amount. Then we did again some filtering, and still actually we doubled the amount of data because we want to save the original one. So now we have less noise. We did segmentation, brought it down to one or few bits, and then the data starts to get more handleable than we had before. But this is still just identifying regions as they belong to something or not belong to something, but we haven't measured anything yet. So now is the question what we want to do. We want from the images extract single numbers or a few numbers telling us something. Could be the volume fraction, could be cell counts, cell stretch, for example, cell volume variability. And with that, we can see with the imaging methods, we can actually now find hidden objects. We can look for dimensions, counting, mixing ratios maybe, or track changes. The change tracking is actually something that comes in a later lecture when I'm talking about time series. But anyway, we need numbers to be able to see these changes. And the metrics that I'm going to talk about now are quite many actually. So we have the surface area, we can count, we can look at some shape tensor, and well, there is a large amount of different metrics we can look at. Some of them are actually more characterizing the general shape. And for that, we have quite some literature. Yeah, so the first one are typically the image processing handbook, which actually shows already a lot. Morphometry with R. I'm not using R, but that's a programming language, by the way, for statistical analysis. And that's kind of competitor to Python. But the good thing about this book, it actually goes through these morphometric metrics pretty good. So I think it's worth taking a look into it if you want to look into these features. Yeah, and then comes something about the shape tensors that we also can look into. There are quite many books on that. And well, as usual, we have a bunch of Python modules. Today, the new one that actually starts being interesting is the scikit image measure. The other ones we more or less had already, I think. The PCA is also new. No? Yes, it is. And the region props is a very interesting function here, which we are going to use. First of all, we need to identify our objects in order to measure something about them. Because in the beginning, we just have a matrix with ones or zeros, or ones and a few classes. And what we want to achieve is actually that we know that this isolated item is item number 1, this is 2, and this is 3. And there is a very nice function for doing that. That is the label function, which is in scikit-image. And it's a very simple method, so it's only, in principle, classes together all the pixels that have neighbors or neighbors with each other, and that brings each label to isolated islands in the image. There is, however, a problem, and that is when you have two objects that are very close to each other, and depending on the resolution, they may be very ambiguous if there is a gap between them or not, and when you segment, they appear as a single object. And this method can't handle that. I think next week I'm going to show you a method that actually can handle it. It requires some more work, but you can actually also handle that problem. So let's look at this image. It's from some database of cityscapes, and you can see some cars here. Some are hidden in the shadow back here, and then you can see here the labeled map that they provided. So these are clear cars, but this one and that one are a bit chopped up because there are trees or poles in between, and that makes it look like there are several objects. So let's look at what we can do with this one. First of all, let's look at this labeling algorithm. It's a function in scikit-image morphology called label. And if we look at the help, one thing that is very important is to look at that we have different connectivities, and that is the neighborhoods that are probed when it tries to connect pixels with each other. So you have, in particular, these two are the most usual ones, where you look into just horizontal and vertical directions, or in two connectivity case, you also look at the diagonals. The label function can actually also work on three-dimensional images, and then you have some more neighborhoods that you can look at instead. Actually, not these, because they don't make sense anymore. Then you have 6 connectivity, 18 connectivity, and 26 connectivity instead for the three-dimensional data. So let's label this image, and here we just call the label function, and out comes this image, where you can see that the first two cars, they are complete, but the labeling doesn't identify these ones as complete cars, and just that's because there is a gap between them. So what we can do, the first very simple thing is we can actually compute the area of each segment, and that is in principle, we loop through the image and count every pixel belonging to each class. And there is an easy way. You can go here through each label that we have, and there is this nice function in Python called unique. It actually extracts all the unique numbers that you have present in the image, and then we just loop over these unique labels, and then we say sum all the pixels that are within this label, and then you get your area for them. A different way, so this is the loop way, and of course you can do it. A different way is actually to use the histogram, because if you make a histogram with as many bins as you have labels, that will actually do the same counting, and then you don't need to do the separation with unique You don't have to loop several times in the image, because this one is actually comparing the image, the whole image, every time. And that one is just one single sweep, so you have some speed up gain in using the histogram. What you need to know, or maybe you need to run the unique to identify the bins that you want to use, but otherwise you can just look for the maximum in the image and see. And I think even the label function even provides the maximum label. So, how does it work? There are many algorithms, more or less fast. This specific algorithm that I'm going to show now is a simple one. It's easy to understand, and it's in principle, if we have an image like this, we have 4 different segments and background. Never forget that background is also a label, given a label. And it's not necessarily that this label is 0, which you could maybe imagine that it should be because it's the background. But like you have in this case, it's actually this one would get label 1, the first label. And then the background would get the next label. So let's look at this and see what we do. So the first part that we do is we actually do an initialization of the algorithm. And the initialization is the index of each pixel. So we number each pixel in the image by 1 to whatever, 81. So every pixel has its own index. It's just a running number through the image. And here you can see the first pixel gets 1, this corner pixel gets a 9, then it's 10 is a 0, then the next one gets 11, and so on. So now each pixel in this image has an individual label, but that's not what we want. So what we need to do is to start this brush fire algorithm that actually is an iterative approach, tries to find connect all those that belong together. And the looping is for all pixels in the foreground, look in its neighborhood, and if it belongs to the foreground, set the label to maximum of the current pixel and the one in the neighborhood. And then you repeat this approach until there is stability, and that comes at some point, and that is when all objects are labeled. And there is a comment actually. This local maximum is actually the same as using the gray level dilation that I mentioned a couple of weeks ago. So it's the local maximum that is computed, and then you don't have to loop that much, and the code is a bit cleaner. So what we do is we start with some initialization, and then we get the main loop where we look at the dilation with some kind of footprint. And footprint is a structure element or tells the neighborhood that we are investigating. And we're going to look into the effect of these neighborhoods later. And the mask is just the foreground mask. And then it iterates and updates until there is no change anymore. So the steps we can see here is in the first iteration we have a lot of small groups and quite many changes in the image. And then after a while you see that the changes reduce, and then you have your final image. So if you look at this one in the first run, it's just the iteration 0, then we just have the initialized. In the first iteration, you can see that the maximum in this diagonal was 31, so that is actually propagated up. And here, the maximum between those is 11, so that is also propagated up. So you can see that it's kind of moving upwards, and in that diagonal. In this diagonal, it's also moving upwards. Here it's moving, all are actually moving upwards, what I'm saying. And then in the next iteration, you can see that 31 is getting dominant. The other ones are shifted out. And in the final, you have 4 different labels, 31, 33, 73, and 81. And that is our final labels. These may be a bit strange numbers. Maybe you want to have only the labels 0, 1, 2, 3, 4. But that is a post-processing step where you would do this mapping afterwards if you want to have it like that. But usually it doesn't really matter what exact label you have. It's just an ID number. So this one algorithm, it actually converges pretty quick in this specific task. It can be more complicated, and then the iteration takes longer. In particular, if you have curvy shapes, then it can be and very much thin shapes, then it's more difficult. And there are a couple of much more efficient algorithms around, and some were actually pretty old. So 1966, the first labeling algorithms were already developed. This is a book that I would really recommend to look at. He also has a labeling algorithm in here. And it's a very good book if you want to go deeper into morphological image processing. Has nice examples. The pseudocode is very clean. So if you are interested in morphological processing, take a look at that book. You can also, I think, all our links to the DOIs, so you can just get them from the different publishers in the ETHNet. Wikipedia also has some information about these algorithms. So there are many sources, many algorithms. And today, also the trick is to do parallel, multi-threaded or parallel algorithms for doing it, because everything must go fast. And as we are looking at neighborhoods, it's not so easy to get a clear idea what happens between different blocks in the multi-threading. So that's also a piece of development that has been done to go towards multi-threaded labeling. So we just had a very simple image, and let's take the brush fire algorithm and look at this image. It's a little bit more complex. So it's more blobs. You have clearly 2 blocks, and you also have a little tail here, which is in the diagonal. And that is going to be interesting to look at what happens with that later. So the first step is we produce all our initial labels. And if we would have 3x3 neighborhood, which labels do you think would be used here for the 2 blocks? It will produce 2 blocks. Think maximum. So this one, 154, will give the label to that one, and 165 will give the label to that one. So that is what they will give. And then we let it run, the brush fire. We say we limit it to 99 iterations. I don't think it's needed. As you can see here, we did only 7 iterations. So it was pretty quick to go through this. And looking at that, I think I need to go back a couple of slides to make sure that I got everything. I think I need that one. No, I need even more. Yeah, let's go back all the way to I thought I had it run, but apparently I didn't. slow. No? Why not that all of a sudden? That is strange. Yes, now it works. That's at least something. So now we can see how this algorithm is growing in regions. And you can see that the 165 is really moving out and shifting out everything in one of the images, one of the blocks. And we have the 154 that also shifts out the other ones. So this looks like the algorithm worked on this object. Now what would happen if we try different kinds of footprints? So now I will do a much larger footprint, a 5 by 5. And here, I need to go back again, just to make sure that it actually happens. And here you can see what happens is actually it's only labeled as a single object. And can anyone tell the reason why it does like that? Previously, we had, yes?
5 by 5 is the number of the neighborhood.
Yes, that's a neighborhood. So it's 5 by 5 pixels that are.
So it's counting also the boxes from the left that is big.
Exactly, exactly. So what is happening is that, I just have to stop it just somewhere. Yeah, about here. So when we have this neighborhood, 5 by 5, looking at this particular pixel, it actually goes beyond the gap and labels, brings over the label to the other side. And that is what happens when you do a larger neighborhood in the labeling. So that can be a way to actually get rid of the problem that you have gaps between the objects like we have here. Sometimes it can actually be annoying, so you have to select the neighborhood depending on what you're doing.
How do you know how many iterations you should do?
Stability. The algorithm doesn't change anymore, and then it's done. So if you can set this n iterations to something, and if you see that there is still things changing, you need, when it reaches 99, then you know, okay, I need to still do something that to increase the number of iterations to get the full labels. But as I said, this is a very simple algorithm. It's good to display the principle. Most algorithms that are used, they are either based on two-way scanning. So you scan once through the image and once back, and then you have it. So you don't need to do this brush fire thing. And then you don't have any limitation of the number of iterations. And I think there is. And then there are some other which is also kind of region growing, so it knows, okay, I have an edge pixel, and then it grows out into that and fills up the object. So different approaches depending on the type of objects you're looking at, which is the most efficient one for your special case. But in this case, it's just repeat until stability. Oh, sorry, I didn't say what we are going to do now. So in this case, we look at a smaller kernel, and instead of a 3 by 3, we only look at the horizontal and vertical components. What you can see as a difference compared to the 5 by 5 is that with the 5 by 5, we only had 5 iterations, and it was done, because it covers so large area. And if we look at this one with a smaller kernel, we need go to iteration 13 before we stabilize. And that's because we have a smaller search area. And That one I think I also need to run, just to make sure that I have it. So, it's done. And now you can see, or actually it's not so easy to see because the colors are almost the same. But now when I use this structure element, you can see that first the 165 takes the big blob, but for the smaller blob, you actually have two labels. You have 140 and 154. And that is because this cross-like structure element cannot go across the diagonal, and here we have a small diagonal, so that it actually doesn't sense that it has a different neighbor here. So that means we get now 3 groups instead of 2 in the 3x3 case. So if you compare them, we have our 3 cases. We have the cross with 13 iterations. We got 3 segments. And we have the 3x3, 7 iterations and 2 segments, and the 5x5, 5 iterations and 1 segment. In the end, I think they do about the same work, even though it looks like it has more iterations. But you get different results in the number of segments. So that is where you need to select what kind of structuring element you need in order to get the kind of labeling you need. So now we have labeled the objects. Now we want to measure things. We want maybe to count the number of voxels or pixels in each label, and then we get the volume. We can also look at changes. So if you erode and dilate your objects, then you can get the surface area. And that you can, of course, do with your own code, but it's much easier to do it with a predefined function, which gives you everything. So what we want to do is maybe count the cells, maybe tell something about these cells, and even in the next step would be to compare cell colonies or something between 2 different images. So the first thing is to measure the position. And we want to compute the center of volume and or center of mass of a single object. So we have now we need to identify an object. So we need a label. Let's say we want to look at the label 1 in this case. And then for doing that, we define our center as the weighted average of pixels in each direction. So you measure in the X direction, Y direction, and the Z direction, and compute the average position in those. And by doing that, actually I took that one. Okay, I took label 2. Anyway, from this one, we can compute with the help of this algorithm. We can compute the center of this volume, and it comes right here. And that is something we usually compute for the objects to know where we have them, and with that we can also already start separating objects depending on where they are. Maybe we can see that some of these objects are clustering in different locations, and then we can tell something about that. And what this little loop here does is actually it produces lists of X and Y coordinates, and this is the output in this table. Creating these tables is more to visualize the coordinates. When you do it in other algorithms, you actually don't produce this list, but you just do the summing and weighting directly. Another one is to compute the center of mass, which is a bit different from the center of volume, because now you introduce also the gray level of the image. So you look at the gray level within this object and tell at the same time what your position is. And then you have to normalize by the average gray level in the object. And from that, we need to do a little calculation. And here we have two images that we have produced. One is the segmented image, and one is an intensity image. And you can see that there is a gradient in it. And this will afterwards shift the position of the center of mass compared to the center of the volume. And that you can see here, where you have the center of the mass is here. So dark is higher intensity. So it actually pushes the center of mass towards that direction. And then the center of volume is pretty much in the center of this square. Depending on what you're doing, you can use either one. Mostly, if you just have gray level, so black and white objects, it doesn't really matter. But if you have objects where you really have a, say, a heavier part, then this can be helpful to find the true center of the object. Instead of, so if you would have some kind of pear-shaped thing, your main mass is still within the big blob, and that will push it more towards the big blob. So, other metrics that we can measure, we already talked a bit about the area, which is just the sum of all pixels. Perimeter length, there are different ways to measure it, but one way is just to do an erosion and subtract the eroded from the original, and then you get the perimeter pixels. I will talk a bit more about those metrics next week when we are talking about uncertainties. No, in 2 weeks when we talk about uncertainties. Sphericity, how spherical an object is. So what you do is you compute the volume of the object, and you compare that to, say, the ideal sphere with the same volume, and then you can get a metric how spherical it is. You can look at the orientation too. So if you have more extended, extruded objects, you can also see the orientations of the objects. And of course, most of them you can easily code, but why do it when someone else did it already? Because there is this region props function that actually gives us all of these metrics and more. And if we look at the region props, you can actually determine which properties you want to compute, and later down here you can even see all the different properties that you could use with this region props function. Here I have listed up most of the properties, and this is all the properties you can look at, which is quite many. And when you look at this gray image that we had before, the segmented image versus the gray image, then you can see all the properties that are computed. And this is, of course, way too much to look at. Sometimes you don't even need all of these, so why compute them? And some of them may be too abstract, and some may be too specific. And the question is also, are they really telling what you want to see? So, for example, if you never ask how long a cell is in the x direction, because the cell could be differently oriented, and then it doesn't really make sense to tell how much it is in the x direction. Also not in the y direction, but what you would need is maybe the medial axis, the orientation of them. Then you can start telling things instead. And that is actually one of the metrics we have. If you go back to here, the major and minor axis length, that would tell you a bit more about these objects, instead of just looking at the box or the area that it gives you. So it's important to identify which properties you actually need, and then just compute those and start looking at those. So instead you can here specify the properties you want to look at. So in this case, I just want to look at area, perimeter, and centroid. And when I have computed that, I can look at those for this specific object. And now we only looked at single object, but it's not what we really want. We want many objects. So we can repeat this for every label in the image. Another one is to look at the extents. So that is just computing a bounding box around the object. So it's in principle just min-max of the positions in each direction, and that gives us the bounding box. So it's a quick way to see where the frame is of the object. And that would look like this on the car item. Let's see. Yes. So that would be how it turns up. And here we can see that the bounding box of this object is within this frame. So we get the x and y coordinates, and that's it. So let's try it. Let's look at all the cars in the car scene, and we want to tell something from them. And now we can compute the region properties for all the objects. So we have the label image, and we want to have information for each label, the centroid, and the bounding box. And if we look at that, we get all this information. We see the bounding box coordinates, the centroid coordinates, and each label. Now we want to look at something around it, and we can even here, we can try to identify them. So we have a frame around each car. We also have a centroid of each car, and that can tell us already something, depending on the objectives of our investigation. This may already be good. In particular, if you're looking at a movie, I would guess this is part of a movie actually, where you want to see and track where each object is and how fast they are moving. And then, of course, we can do a lot of statistics on these. The interesting thing here is actually we can tell the color, so label the color, and that's that one I should have hidden, but okay. So what we want to do is we want to tell the color, the average color of each car, and to do it, we first get the CSS4 colors, which is a standardized list of RGB labels, and they are given a name, and that is the name used on web pages, etc. And now I use that one to train a k-nearest neighbor classifier, and then I fit all these colors and color names together. So that means we have RGB components, and they are clustered into different groups of names. Now we want to use that to predict what is the color of each car, and then we get here what the different colors are. So everything is grayish actually, which is quite boring. But if we look at that, we can see that this one is supposed to be dim gray, that one is silver, it's a bit brighter. Dark slate gray, dim gray. That one is a little bit more bluish, so it was then classified to be blue. Good or bad classification, that can be discussed, but it's a way how you can actually classify the colors of the different segments. Probably you should also do, I only had here, I had only one neighbor. Maybe we should increase the number of neighbors to get a better classification. Or it may be more confused, I don't know. But anyway, this is a way how you can actually label the colors. So if you are into color labeling of things, this would be an approach. Another thing is we have objects that are perfectly round or a little bit extruded. And for that, we need to describe how this is. And the anisotropy is, there are different ways. So there is a definition. varying magnitude in proportion according to the direction of the measurement. So if you measure this one, you have one long and one short. And with that, we can put some fuzzy wording on it, tall and skinny, short and fat, or perfect round, something like that. But we want to put a number on it instead. And to put a number is not completely straightforward because we want to have some ratio between shortest, longest, but what is it? What actually tells something that for us? So here is a long list of different options. So we can take the longest by the shortest or subtract one. We can take the shortest minus, no, longest minus the shortest divided by the longest, and so on. So you can be very creative in these, and probably in your different fields, you will probably have a definition already what is the anisotropy metric that suits your work. Or you have to test some different things and see where you can have a good separation between different objects. So here is a little code. I defined the different side lengths, and we try to compute these and see what happens. And here I have to go back again. So, and next. So here you can see this shape goes from perfectly circular to just a straight line, and you can see how these different metrics, how they behave. So for example, the first one goes in principle to infinity when it's thin. So it has the range from 0 to infinity. Other ones, they are more bounded, and you can see how much they raise. And this is actually where you can have to decide which type of anisotropy you want to work with, where you have the sensitivity in the range that is relevant to you. Then we have some statistical tools. This is quite a massive piece actually, and what we do here is we combine two different topics. One is linear algebra and the other one is statistics. And with that we can extract interesting information from the objects, and even though they don't seem to be so connected in the first view. But what we can do is something called principal components analysis. And in principle, we try to identify different clusters with the help of this method. And the clusters, they are not really physical or really related to the objects, but you can see which mixtures are maximizing the sensitivity. And what we do, the steps are in principle, we compute the covariance matrix between our different features or different images of some kind. And from there, we do eigenvalue or singular value decomposition. And we can use the eigenvalues as measure how important each component is, and we can use eigenvectors to transform the data. Still may sound a bit abstract, but let's look at it. We have some spectra here. This is just simulated, but anyway, we have a spectrum for noise, we have a spectrum for fat, and a spectrum for proteins. And you can see here there are some common bumps, but in the case of the protein, there is yet another peak in the data. And now we want a way to separate these in a smart way. Given the noise, you have several measurements. Sometimes there is a lot, sometimes there is a little. And now we want to see if the components are more fat-like or protein-like. And for this, we generate 20 noisy spectra of each type. They're not so easy to distinguish. You can see here. It is quite jumpy in the data, and if you try to plot two different curves against each other, you can see that there is no clear separation at all between them. So now we come in with this principal component analysis. We run with 5 components, and let's see what happens. First is, if we look at the eigenvalues, we see that most of the information is actually within the first 2 eigenvalues. And that gives us first a good separation that we can probably describe or separate this data with only 2 components. That's a good thing. In other cases, principal component analysis is actually used also as data reduction. If you have a lot of data, you can reduce it to less components using a discriminator at this point. So let's do a transform. So now I take the eigenvector matrix to transform all my spectra. And now we can see here we have 3 different components. The first 3, so that would be eigenvalues 1, 2, and 3. And we can see here what kind of signals we get. And it looks like we have some separation in all this noise. So the third one seems to be pure noise. But the other ones, they are much clearer. And if we try to plot component 1 and 2 together, we see a very beautiful separation between all these 3 classes. And now from that, there on, we can do, for example, a k-means clustering, and we would easily identify 3 clusters. Problem is, when you do it, is you always need to normalize your data, otherwise you will see similar things that we saw with the k-means in one of the previous lectures. Another thing is, when you have these low intensity eigenvalues, don't try to put too much interpretation in it, because it's essentially noise in them. And then it's also important to look at the signs in the data, because it can be a bit misleading. One example that I have is to look at crystal textures in metals. Here we look into Bragg edge imaging, so that is energy resolved imaging, in my case now with neutrons. And what we can do is we can probe for the Bragg criteria if we have a constructive or cancelling interference within the crystal grating. And with that, we get a very characteristic pattern for each element or each kind of crystal that we have. And we have here, for example, one ion face-centered cubics gives you a very characteristic pattern like this over the energies. And if we scan over these, we can see that there is a clear distinction between these 2 objects. And that is used, for example, here it was 3D printed ion pieces. And looking at the average image, you don't see much. You just see that we have some spacer, we have the material, and we have air in this area. If we look at a single wavelength, we also don't see much. But when we start applying this principal component analysis, you need to do a lot of data preparation and run the PCA with 5 components in this case, and do the fitting. Then we see that we have, first of all, actually this is logarithmic scale, so most of the information is actually in the first component. Then there are some few percent in the second component. And if we start looking at these components separately, they look a bit weird. And if I plot it the same way as I did before with these synthetic spectra, it doesn't come out as nice as before. And that is for one reason, because we have so much data. And instead, if I just set the transparency of the data, we can start seeing that, we have one clear blob here. We have 2 stripe-like blobs here and 1 or 2 over here. So we can actually separate information about this sample. And that can be used for one as a color coding. So now I use the first 3 principal components to use them as RGB in a color coding. And by doing that, I get an image like this, and that actually shows that there are some special things happening around the surfaces of these objects, and that was actually the question in this investigation, because I did a surface treatment with, I think, with a laser to harden or change the structure of the object, and that can be nicely visualized when you do this kind of reduction. And well, here they are together. And that the next step would be actually to do some kind of segmentation. We could try to apply the k-means, I would guess, to do this, to identify the regions which have been worked out. Yes, I think I need to stop. Let's make a break. Yeah. I think I have quite a lot of material today, so let's just do the break until 1:15 again. So when the clock clings, then we go on.